Okay, Assalamualaikum and good morning, everyone. I hope you guys are doing well after a long, not so called holiday. So, I started to uh, forget what should I taught you guys, what should I teach you guys this week. So I hope we have finished the slide before this, the introduction to root locus. And for today, we are going to learn about how to sketch root locus by understanding some properties of root locus. Okay, so basically in this lecture we are going to look at some properties of root locus and how to find the properties from transfer function, and then we can sketch the root locus without using the table method that I explained in the lecture before this. Okay. Okay, so after completing this topic, this lecture, the students or you all will be able to sketch a root locus by applying rules for a refined root locus sketch, and then determine some important properties such as the asymptotes, breakaway, breaking points, the JW axis crossing, and the angle of departure and arrival. We will look at this more detail after this. Okay, so let's take a look at an example of a transfer function and how we can sketch a root locus from this transfer function. Okay, so let's say you have a feedback transfer function, I mean a closed loop block diagram that has a gain k and a forward transfer function gs and a feedback transfer function hs. So before we can draw this, the root locus, we need to find the closed loop transfer function, meaning that we need to simplify this block diagram first. So we can simplify by using the feedback formula. And after simplify, we get this transfer function, okay? So this transfer function, we will look at the denominator because our root locus basically is the plot of poles. Okay, so when you change this k value, what happened to the poles? Okay, so we need to look at the denominator first. So the denominator is this one plus k times s plus 1 times s plus 3 over s plus 4 times s plus 5 times s plus 2. So from this transformation, we can further simplify from this equation. Then we get this equation that we want to find the poles after we change the k value. So the idea of root locus is we want to plot this equation when we change the k value from 0 to infinity. So the root locus always start from the value of k equals 0 and then ends when k equals infinity. So this is an example. So from this transfer function, from this equation, we can find the value of k equals 0. So when k equals 0, we can find the poles, or the value of s equals -2, -4, and -5. And these are the poles of the forward transfer function, or poles of this closed loop transfer function, poles of this closed loop transfer function. And then we can plot the value of s when k equals 0 on the s plane. So we get -2 here, -4, and -5. So because it's a pole, we use cross. And then we find the value of s when k equals infinity. So when k equals infinity, we get p1 equals -1, -3, and another one is equals infinity. And these are the zeros of the closed loop transfer function. So we can plot them on the S-plane using circle symbol. And fortunately for this root locus, the red arrow here are the sketch of the root locus. Okay. So later on we will see more example about the sketch of root locus. But for this example, the root locus are these red arrows here. So the root locus, the shape or the bentuk dia is as shown here. Okay. So the idea for this slide is that to find the poles, we can substitute k equals 0, and to find the zeros, we can substitute k equals infinity. Okay, so these are the other ways you can find poles and zeros. Okay, so let's look at some rules. So there are 8 rules to sketch a root locus. So rule number 1, so the number of branches of the root locus equals the number of closed loop poles. So for example, in this root locus, example of this root locus, we have 2 poles, one at 0 and the other one is at -10. Okay, so our poles at 0 and -10. So we have 2 poles here. So because there are 2 poles, meaning that there are 2 branches of the root locus. So dia ada 2 garisan saja, dia ada 2 graph or branch. So one of the branch is starting from this 0, value poles equals 0 and going up. This is one branch. And the other branch is starting from this pole equals -10 going down. So this is the second branch. So if you have 3 poles, then you have 3 branches of root locus. So 2 poles, 2 branches. Okay, so that's rule number 1. Now let's look at rules number 2. The root locus is always symmetry about the real axis. So this is again example from previous slide. So if you look at this root locus, it is symmetry about the real axis. Okay, so this is the real axis or the x-axis. So if you want to draw the root locus, you must make sure that it's symmetry about the real axis. And then rule number 3, the root locus begins at the finite and infinite poles of GH and ends at the finite and infinite zeros of GH. So to simplify this rule, your root locus will begin at poles and then ends at zeros. Okay, so always start your root locus from the cross or the poles, and then it will end at zeros. Okay, or the circle. So here, meaning that your root locus has a sort of like direction. So we represent the direction by using this arrow. Okay. So when you sketch your root locus, please include this arrow to represent it starts from poles and then ends at 0. Okay, so here in this figure, we have 2 poles, one at -1 and the other one is at -2. So we have 2 poles, meaning that we have 2 branches. Okay, so we have 2 branches of root locus. And here we have 2 zeros, one at -3 and one at -4. So your root locus will start at pole and ends at a 0. Okay, so in this example, your root locus starts from let's say -1, and then it will split, one going up and the other one from -2 going down, or maybe -2 going up or -1 going down. And then it will go here, and then it will split again, one going to 1 0, -3, and the other one is going to the other 0, -4. So here the sketch consider also the symmetry. So if you look at this shape here, it's a circle, symmetry about the real axis. And then because you have two poles, it must have two zeros as well. Okay, because of rule number 3, the root locus will start at pole and then ends at 0. So it will start at one pole and then end at 1 0. So it cannot start at one pole and then going to two different zeros. So it must start from one pole and then end at 1 0. Okay, or it cannot start with two poles and then going to one common 0. Okay, it will go to two separate zeros. So that's why here we have two poles and two zeros. And then rule number 4, on the real axis, the root locus exists to the left of an odd number of finite open loop poles and zeros. Okay, so this rule is kind of confusing. So what it means is that when you determine the number of poles and zeros, for example, in this example, we have a pole -1 and -2, and 0, -3, and -4. So to determine the root locus that you must draw on the real axis, so when you draw the root locus, there are some part of the root locus will be drawn or light on the on the real axis. So to determine which section of these poles and zeros that has the root locus on the real axis, okay, only on the real axis, you need to determine, you need to calculate how many poles that you have. Okay, for example, starting with this one, so at -1 here, from this line here to -1, there is no poles here, no poles or zeros. Okay, no poles or zero here. So when there is no poles or zeros, meaning that there is no root locus on this real axis. And then at this section here, at this range, we have one pole here, okay, before reaching -2. So we have one pole at -1. So because we have only one pole, meaning that we have one or odd number of pole. Okay, ada satu is odd. Okay, one is odd number. So we have a root locus that should be drawn on this real axis. And then on this range, so we have two poles here before reaching -3. So because we have two poles, so now 2 is an even number, so it's not odd number. So we don't have any root locus on the real axis. And within this range, -3 and -4, so we have two poles and 1 0 here. So meaning that we have three poles and 0. So 3 is an odd number. So we have a root locus on the real axis. And then lastly, this section. So we have four things here, two poles and two zeros. So we have 4. So 4 is not an odd number, it's an even number. So we don't have any sketch on the real axis here. Okay, so don't worry if you don't understand. Maybe later on I will explain more as we do exercise or tutorial. Okay, rule number 5. So the root locus approaches a straight line. We call it asymptote. As the locus approaches infinity. And to determine the asymptote, we need to use the equation of the asymptote, which is given by. So to find the real axis intercept of the asymptote, we use this formula. So the real axis asymptote equals the sum of finite poles minus the sum of finite zeros divided by the number of finite poles minus the number of finite zeros. Okay, so the hashtag here meaning number, okay? The number of. And then we can also find the intercept angle or the angle of the asymptote. So the angle theta A equals 2k plus 1 times pi divided by the number of finite poles minus the number of finite zeros. Okay, let's look at an example how to use this formula and how to determine the asymptote of the root locus. Okay, so let's say you have this transfer function, forward transfer function in a unity feedback system. So firstly, we need to determine the poles and zeros of the closed loop transfer function. So for a unity feedback system, okay, so only for unity feedback, we can determine the poles and zeros of the transfer function, of the closed loop transfer function, by looking at the forward transfer function only. Okay, so the poles and zero can be determined straight away from this transfer function, only for unity feedback system. Okay, but a non-unity feedback system, you need to simplify the block diagram, and then you use the concept when k equals 0, you get the poles. When k equals infinity, you get the zeros. But for unity feedback, you can determine the poles and zeros straight away from this forward transfer function. Okay, so here the poles are s equals 0, minus 1, minus 2, and minus 4. So we can sketch the value of poles on the s plane. So equals 0, minus 1, minus 2, and minus 4. And then the zeros are or is s equals minus 3. Okay, so we only have 1 0 at minus 3. Okay, so to calculate the intercept, real axis intercept of the asymptote, we use this formula. So the sum of finite poles, we have minus 1, minus 2, minus 4, minus 0. So we sum them up. Minus the sum of finite zeros. So we only have 1 0 at minus 3. Divided by the number of poles, we have 4 poles minus 1 0. So we get the intercept, real axis intercept at minus 4 over 3. So this value is represented here. Okay. And then we can find the asymptote angle. So we use this formula 2k plus 1 times pi divided by number of finite poles minus number of finite zeros. So what is the value of k? So we start the value of k from 0, okay? So k equals 0, 1, 2, and so on, okay? So first we assume k equals 0. So we get theta A equals pi over 3. So the pi over 3 is this angle. Okay, okay, so this angle here is pi over 3. Okay, pi over 3 represent the first asymptote starting here and going up. Okay, and then we increase the value of k from 0 to 1. Okay, so we assume k equals 1. So we get theta a equals pi. So the second asymptote is measured from here to here, pi. Okay, so the second asymptote starting here, going to negative real axis. And then we increase the value of k. So we use k equals 2. We get the asymptote angle at 5 pi over 3. So this angle here. Okay, so the third asymptote starting from the intercept going downward. Okay. So we can further increase the value of k. So let's say we increase k equals 3. So what we get is theta a equals 6, 7 pi over 3. So now 7 pi over 3 is actually bigger than 2 pi. So when you calculate theta a later, you get a value bigger than 2 pi, then you stop calculating. Okay, meaning that we need to find theta a, the value less than 2 pi. Okay, so here we get theta a bigger than 2 pi for k equals 3. So we stop calculate. So meaning that we stop increasing the value of k. Okay, so here meaning that we have 3 asymptotes. So one asymptote at pi over 3, the other one is at pi, and the other one is at 5 pi over 3. And the real axis intercept at sigma a negative 4 over 3 over here. Okay, any question before we go further? Okay, boleh tanya soalan?
Sir,
Yep.
macam mana kita tahu dia punya arrow tu, sir? Yang contoh yang dekat kosong dengan negatif 1 kan dia ada arrow yang bertemu.
Yang ni ke?
Ada arrow yang ke kiri, ada arrow yang ke kanan.
Okay, yang ni kita kena buat tutorial minggu depan. Sebab yang arrow ni dia kena susah nak explain sekarang lah sebab dia ada rules lain lagi nanti. Tapi nanti tutorial minggu depan we will go back to the same question, rasanya same question with this one. And then kita akan tengok macam mana nak draw the arrow. Okay.
Okay, sir.
So for now remember the rules first, understand the rules, and yang arrow tu kena tutorial kot rasanya.
Yang angle tu dia yang sebelah luar, sir. Angle.
Angle ni just nak untuk kita tentukan asymptote ni dekat mana. Maksudnya root locus ni bila kita when we extend this root locus, so it will not cross the asymptote. Okay, dia akan macam menghampiri asymptote. Tapi kat mana asymptote tu? The angle here is to determine the asymptote lah, the location of the asymptote. So asymptote tu macam satu garisan yang panjang. It's just a straight line starting from this point here, the intercept, and going to infinity lah. Dia akan satu garisan yang panjang. So your root locus tak boleh lah lukis dia macam ni. Maksudnya tak boleh cross the asymptote. So the root locus will never cross the asymptote. Macam tu lah.
Okay, sir.
Okay, so far we have 5 rules. So rule number 1, number 2 until number 4 is doesn't involve any calculation, but involve or to theory. Okay. So rule number 5 will involve calculation because you need to determine the asymptote, real axis intercept, and the angle, and you need to sketch the asymptote as well, so that when you sketch the root locus, it doesn't cross the asymptote. Okay, so starting from rule 5 until rule number 8, it will involve calculation. Okay, so rule number 6 is known as the JW axis crossing. So for example, in this root locus, we have the root locus crosses the JW axis. Okay, so it crosses this axis. Okay, so how to determine the JW axis crossing? So we know that from lecture number 3 kot, tak ingat dah. So we know that when the poles are located on the JW axis, then the system is marginally stable. Okay, so when the poles are located here, the systems are stable. And when the poles are located on the right hand side of the S-plane, the system is unstable. But when the poles are located on the J omega or the JW axis, then the system is marginally stable. It's either stable or unstable, meaning that it will keep oscillating. Okay, it doesn't increase in value or doesn't decrease in value. So the JW axis crossing is an important point that you need to determine to understand whether the system at what value of k the system is marginally stable, so that when you keep increasing the k value, you will not get the system to become unstable. Okay, so to determine this JW axis crossing, you can use Rapp-Hurwitz criterion. Okay, harapnya tak lupa benda Rapp-Hurwitz criterion. Okay, so example. So this is a similar example to previous example in rule number 5. So firstly, we need to simplify this block diagram so that we can get the denominator. Okay, so to use Rapp-Hurwitz criterion, we need to have the denominator of the closed loop transfer function. Okay, simplify the block diagram, take the denominator, and create the Rapp-Hurwitz table. Okay, so we calculate the table. And then the pure imaginary roots only exist when there is zero row. Okay, so when there's a row full of zeros, meaning that the system is marginally stable. So only row S1 can have all zero in the entire row. Okay, because we have zero here and zero here. Okay, so row number 4, we cannot have all zero. Row number 3 as well. And row number 2, we can have, but only when k equals 0. Okay, so only one value lah. So if k equals 0, then 90 minus 0 is not 0. Okay, so we cannot have entire row 0 for s power of 2. So the only row that can have all 0 is S1. So S0 can also, but tu cerita lain. So kita assume S1 dulu. Okay, so we take row S1 and we find the value of k for this thing here becomes 0. So there will be two value of k because it's a quadratic equation. This one is quadratic equation. So there will be two value of k. So we take the positive one, okay? So we take only the positive. So the other k is a negative. I think it's a negative. So we discard the negative k. So we take the positive k. And then we take this k value and use it, substitute the k into row s squared. So we first build this equation here. 90 minus k. So this row here, this column here. 90 minus k s squared plus 21k equals 0. And then substitute the value of k from row S1 that we found earlier. And then from here, we find the value of S. So we get S equals plus minus 1.59 times J. So the system is stable for K from 0 to 9.65. And at K equals 9.65, the system is marginally stable when this is the J omega crossing. Nota pun tak lengkap pula jadi. So to find the frequency, we use the S equals J omega, okay? Okay, so J omega. So this is frequency. Rasanya ni salah kira. Okay, salah kira. Maaf kat situ. So the frequency is 1.59 radian per second. Okay, so this is the frequency of the oscillation of the marginally stable system, in which the system will keep oscillate, okay? So the oscillation of the system is at frequency 1.59, but the gain at that point is equals 9.65. Okay, so the rule number 6 to find the J omega crossing is first generate the Routh-Hurwitz table. And then find the value of k, usually at S1, okay? And then third, use k on S2. And then number 4, find S from number 3. Okay, more example in tutorial next week, inshallah. Okay, so this is the to determine the J omega crossing. So to determine J omega crossing, these are the steps, okay? So you need to familiarize yourself with Routh-Hurwitz criterion. So if you still don't know how to generate the table, silalah study. Okay, now we move on to rule number 7, the breakaway and breaking points. So let's say if we have this root locus. So in this root locus, soalan yang tadi lah, macam nak tahu dia tiba-tiba keluar, dia macam anak panah tu, and then dia tiba-tiba terkeluar dari real axis. So that thing is known as breakaway and breaking points. Okay, so breakaway points is when the root locus going out from the real axis. And then the breaking points is when the root locus coming back into the real axis. Okay. So this breakaway and breaking points is always at an angle 90 degree. Okay. So angle dia 90 darjah. The angle is measured here. Okay, dia punya tangent. So the tangent of the circle at this point is 90 degree. Okay. So breakaway point is when the root locus breaks away from the real axis, while breaking points when the root locus breaks into the real axis. So how to find this exact point here, point A, and this point, how to find this exact point? So this is rule number 7. So how to find breakaway and breaking points? So this is the formula. So the summation of 1 over sigma minus zeros equals the summation of 1 over sigma minus pole. So Z1, Zi and Pi are the negative of 0 and poles values. So sigma here is our breakaway or breaking points. Okay, so bolehlah buat tutorial untuk formula ni. So let's look at an example from the similar root locus for rule number 7. So in this root locus, we have poles at -1 and -2. And we have 0 at 3 and 5. So to use this formula, so 1 over sigma minus 0, so 1 over sigma minus 3. So the first 0 is 3 plus 1 over sigma minus 5. Okay, 5. The second 0 equals 1 over sigma plus 1. So 1 minus 1. So we get plus 1. Plus 1 over sigma minus 2. Okay. So we get plus 2. Okay, so if you have 3, 0, then you add another one here. Something, something. Okay, so here the formula means that if you have 2, 0, then 1 over sigma minus the first 0 plus 1 over sigma the second 0. Okay. And then simplify. Ni setiap semester student akan tanya, sir macam mana dapat begini? Ni matematik lah. Okay, saya lecturer AC. Walaupun tahu matematik, bolehlah cari lecturer maths untuk ajar. Okay, ni simplifykan the pecahan. Okay, simplifykan the pecahan. Lepas tu bawa kiri kanan. Dapat lagi ni. Kalau tak tahu macam mana dapat ni, kira slow-slow. Jangan laju-laju. Okay, after you get this equation, solve for sigma squared. So you got 2 sigma here. So the first sigma, negative 1.45, represent this point. And the second one, 3.82, represent this point. Okay. So for rules number 7, this is the formula. And sometimes in your root locus, it's not always have breakaway or breaking points. But that one, to determine whether a root locus has a breakaway or breaking point, that one will involve understanding about the root locus punya shape lah. Okay, dia punya shape macam mana. Later in tutorial, we will see. I think there will be an example when there is no breakaway breaking points. I'm not sure. but we will see about it in tutorial how to determine. Okay, so that's rule number 7. And then lastly, the rule number 8 is the angle of departure and arrival. So the angle of departure and arrival are only for complex zeros and poles. So if you have a complex poles and complex zeros, then you only determine the angle of departure and arrival. If you don't have complex poles or zeros, tak payah cari angle of departure. So what is complex poles and zeros? So let's say if your poles, you get -1 plus j and -1 minus j. So these two are complex number. While the first one here, -3, is a real number. Okay, it doesn't have the j part, okay, the complex part, the imaginary part. So we only care about these two complex number. Because we have this complex number, then we have the angle of departure. Okay, so for angle of departure is for complex poles, while the angle of arrival is for complex zeros. So in this example, we have complex poles only. So we only have angle of departure. We don't have angle of arrival because we don't have complex zeros. So to calculate the angle of departure, these are the angle, this angle, these are the formula. And because of symmetry, rule number 2, I think rule number 2, symmetry. Because of symmetry, 1 minus 1 plus j is located here, while -1 minus j is located here. Okay, exactly mirror image about the real axis. So the angle of departure, which is this angle, theta 1 here, is exactly equal to this angle, theta 1, the red one here. So because of symmetry, we only need to calculate the angle for one poles only. Okay, we don't need to calculate for the pole below here. We can only calculate for the pole on the above. Okay. Okay, because of symmetry. Okay, these are the formula for angle of departure and arrival. Okay, so let's look at an example. So let's say open loop poles are -3, -1 plus j, and -1 minus j. And the zeros are -2 at infinity and infinity. So find the angle of departure. So firstly, to find the angle of departure, you need to sketch or plot the poles and zeros on an S-plane. Okay. So here we plot all of these values on S-plane. So -3 here, -1 plus j, -1 minus j, and -2 here. So we plot them first on an S-plane. And then after that, we find the angles made by the other poles to the pole that we need to determine the angle of departure. Okay, meaning that the angle of departure is this theta here made by this pole. So to find this theta, firstly, you need to measure the angle made from this pole, from this zero, and from this pole to this point. Okay. Cari angle dia dari titik ni ke titik ni dari titik-titik lain. Okay. So for example, theta 1 is just 90 degree sebab dia duduk kat bawah je. So theta 1 is 90 degree. Theta 2 is here. So you need to use theorem trigonometry. So the angle you can get tangent minus 1, 0.5. And lastly, theta 3 is this angle. So again, use trigonometry. We get tangent minus 1, 1. So use the formula from the previous slide. So sum of angle from poles minus sum of angle from 0. So theta 1 is angle from pole. Theta 3 is also angle from pole. And theta 2 is angle from 0. So sum the angle from pole minus angle from 0. So calculate, you get negative 251 degree. So if negative, it's actually measured from here to here. So you make the positive, yeah. You take the positive one. So 360 minus 251, you get 108.4. Okay, so these are the rules for sketching a root locus. For example, what example? Okay, any question before we look at one example? I think it's better if we look at example because tak nampak kan benda lah rules ni. Okay, so let's look at example 1. Okay, so let's say you have a forward transfer function for a unity feedback system. Okay, so a unity feedback system, and this is the forward transfer function. So a unity feedback system, as I said earlier, we can find the poles and zeros just using the GS without assuming k equals 0 or k equals infinity. Okay, so in this question, determine the root locus sketch. Okay, you need to sketch the root locus and then find the asymptote, find the JW axis crossing, and find the value of k when the system is marginally stable. Okay, so let's look at this one by one. Rajunya. Okay, so firstly, determine the poles. Okay, poles. So just use GS. So poles here S equals 0, minus 2, minus 3, and minus 4. And then the zeros, S equals minus 1. Okay, this is rule number 1. Determine the poles. And then rule number 1 also state that the number of branches of the root locus equals the number of closed loop poles. Okay? So here we have 4 poles. So meaning that our root locus has 4 branches. Okay, so we must have 4 branches for the root locus. Okay, so that's rule number 1. And I think rule number 2. Rule number 2 state that the root locus will start at a 0, a pole, and then going to 0. Okay, ends at 0. But here in this calculation, we have 4 poles and 1 0. So takkanlah semua poles ni akan pergi ke 1 0. Okay, so we need to add something. Okay, we need to add an extra zeros so that the poles we have an equal number of its pair. Okay, pasangan dia zeros. So here to add extra zeros, so we just add zeros at infinity. So here meaning that one of the poles will go to one of the 0, while the other 3, it will go to the infinity. So maybe the sketch will look like something like this. Okay, so 0, -1, -2, -3, -4. So maybe one of the pole will go to 0, maybe macam ni. While the other three maybe one going up, one going down, and the other one going to infinity. Because it will need to find the partner, dia punya pair, dekat infinity. Okay? While one of the poles will go to -1. Okay, maybe the sketch macam ni. Or ada bentuk lain, kita tak tahu. Okay, mungkin macam ni. So this branch, one branch. This is two branch, the third branch, and fourth branch. So there are 4 branches. So validate the rule number 1. And then this is going to infinity. Infinity as well. And infinity. So one of the poles going to -1 and the other going to infinity. So the other beginning and ends, okay, at different zeros and different poles. And this is also symmetry, okay. So this is a rough idea or rough sketch dulu before we can further calculate the different properties. Okay, so maybe in your exam, you can do something like this, okay. Sketch dekat kertas kosong lain, like what the root locus will be look like, okay, will look like before you can actually sketch the root locus, okay, macam lukis secara kasar, okay, roughly, okay, draw roughly, sketch roughly the root locus. Okay, so now let's look at the answer. So we found the poles and zeros from the transfer function, and we sketch on the S-plane. And then we determine on which real axis or which range of the real axis has the root locus. Okay, so this is rule number 4, I think. So here, starting from this point to this pole here, there is no pole, okay, or 0. So there is no root locus on this range. And from this range, we have one pole here, meaning an odd number. So we have a root locus located on this real axis. On this range, we have one pole and 1 0. We have 2 things. So it's an even number, meaning that there is no root locus on this axis. On this range, we have 2 poles and 1 0. So it's an odd number, okay, odd amount of things. So we have root locus here. On this range, we have 3 poles and 1 0. So there are 4 things, meaning that we don't have root locus on this axis. And lastly, from -4 to infinity, we have 4 poles and 1 0. So we have 5 things, odd number, meaning that we have root locus on this part of the real axis. Okay, so that's from rule number 1 to number 4, we can get roughly where the root locus should be. Okay, so we have this red colored line here, but the root locus is still not fully sketched. Okay, and then using rule number 5, which is to determine the asymptote. So we can get the real axis intercept at -2.67. So it should be somewhere here. Okay. Alah, salah. Sini. And then we find the angle of asymptote. So we get pi over 3, pi, 5 pi over 3. And at L, okay, ataupun K, okay, L equals 3. We get theta A bigger than 2 pi. Okay, so it's bigger than 2 pi, so we stop calculating. So we get 3 theta, okay? We get 3 asymptotes. So the first asymptote is the green line here, and the other one, and third one. So the angle is this, okay? Kita look ya, serabut. Okay, so this is the 5 pi over 3, the pi, and 5 pi over 3. So we know that the root locus will break somewhere here and then break out, okay? Break away. But where will be it crosses the j omega axis? So we need to determine, okay, the j omega axis crossing. So it cannot break here. Kalau break here, dia akan cross the asymptote, which is wrong, okay? So it must break before the intercept so that it won't cross the asymptote because it has j omega axis crossing. Okay, so this is roughly the sketch of the root locus. So let's look at rule number 6. So rule number 6 is about finding the j omega crossing. So first we simplify the block diagram and get the closed loop transfer function so that we can get the denominator of the closed loop transfer function. And then use Rabb-Hurwitz table, generate the table, and find the value of k when the system is marginally stable. So we use row S1. Okay, row S1. So we get k here, 202. So we take the positive. And then use this k on row S2. So we get the j omega crossing or JW crossing at 5.02J. So the system is stable. Tak tahu dia salah kira kot. Okay. Please check. And the value of j omega crossing is at 5.02. So if you look at previous slide, dia dah lukis crossing dia kat sini. Okay, so your root locus must cross this j omega crossing at this exact point, okay, 5.02. Okay, so that's how you determine the j omega crossing and sketch the root locus. Okay, so in this example, it doesn't determine this breakaway point here. Okay, kalau rajin, try lah cari breakaway point ni. Okay, so in this example, it doesn't requires you to find the breakaway point. Okay, based on the question, it doesn't ask you to determine the breakaway point. Okay, any question? We will continue more next week on the next example. Any question before we end this lecture? Okay, so if you don't have any question, then see you again next week, inshallah. Assalamualaikum and goodbye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.